Welcome to reality. 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 Welcome to reality.
Hello and welcome to reality. And in reality, we're a little bit late. Well, we're your hosts, TechTranslate, and myself, NOPEGENX. We tackle flat Earth misinformation spreading through social media. Now, I generally keep an eye on YouTube and Facebook while TechTranslate is focused on X. It's a late night. In each episode, we'll be looking at one subject and going through its reality with you. So join in the chat, ask questions. We'll look to try and answer them as we go. And let's introduce my co-host, Tech. How are you?
Yeah, quite fine. A little bit dizzy from the intro, but no, I'm fine again. Yeah,
that's reality. See,
Mm.
some lovely people coming in already. Look, Jamie, hi. Thanks very much for joining. And I think you're my newest sub, so well done. Thank you. And we have from the comedy show. Now, this lovely lady done some work for me in the past, and I'm quite eager to get on one of her shows at one point. Please just drop your link if you want to put it in there.
Okay.
So what have we got planned?
Yeah, today's subject is motion. Basically, this is very often misunderstood by flat earthers or by science deniers. Our Earth is spinning, our Earth is flying around the sun, and our sun is flying around in the galaxy. So their claim is we must get dizzy. We should feel all these forces, acceleration and rotations. And we will break it down. How much is it really? How does it influence us? No? And the main point of the misunderstanding is very often the sheer size. Earth is very big. Sun is very big, solar system is very big, and a lot of things.
It's not just very big, is it? It's huge.
Yeah.
It's literally galactic, and universal.
Yeah. And a lot of things from our common knowledge, from the small size, or let me say on a small scale, if we directly put them on the large scale, the large scale is counterintuitive sometimes. No? And I think this is also the main reason why this misunderstanding is there. They transfer directly thinking from the low scale to the large scale. Mathematically, it's the same. You can use the same formula. I will show this. But in the end, it's counterintuitive. No?
Yeah, it's the whole thing of where they show a tennis ball with water coming off it and think it's going to be the same as a planet which has gravity because it's like so much bigger than a tennis ball.
Yeah,
and they're literally where they say, "Show me an example." It's impossible without creating a whole Earth with a moon and a solar system and gravity and reality in tow.
Exactly, and this was also our last subject was the horizon. This has also to do with misunderstanding of scale, and we make a very short recap what happened.
I understand. Time. So since then we've had a little bit more clarification, haven't we?
To
forward.
So I
over
will
to
share. You. I will. So I have to
not do that.
Present.
Everything's gone a bit dark. Yeah.
Which 1 second.
Where are you?
So now I understood where to click.
Is that
Can
what you
see
wanted? Is that
You
what
see
you
my
wanted?
yeah. You see the screen, yeah? Okay.
Yeah,
Okay, I will
we're all
enlarge it
good.
now.
Let me. Do you want me to make it full screen so people can see
Yep.
it at home? Yeah, there
Now
you
it
go.
should work. Yep.
There you go. That'd be a bit easier for everyone.
Yeah. Okay, this is a short recap. Last time we had as subject the horizon, and there came a lot of comments. I made a few slides regarding this, and here one comment was, for example, there was a similar image or like this. Now you have the guy standing here, and he's looking down to the horizon, and the question was, how much has he to look down? You know, if we see the size here, he is a tenth of the Earth radius. In reality, the Earth radius is more than 6,000 kilometer, and we are about 180 high, tall. So basically, from the size here, it's completely different. This is only a visualization. But the
This is
question was,
not to scale, is what we'll say, isn't it? It's not to scale, but the values are correct.
This is difficult for them to get. Also, they claim always, okay, we should have to look down to the horizon. No? And okay, we did this last time, the calculation, how far is the horizon away? We do it basically with Pythagoras. I will now not go too far in the math, but if
they can look at that, and they can look at the previous episode.
Yeah.
Look at that detail. We went into that in quite detail.
Yeah. And later on, I will show my X account where you can see all the slides and take your time to go through it and correct me if I made a mistake, of course. No? And here, basically, this would be the straight line of sight. And this is the side down to the horizon, or side down to the horizon. And if we do the math, we get an angle of 0.04 degree. So basically, it's 1/400th of a degree. Now, so basically, it is not noticeable. This is why we basically see when we're standing on sea level, that we see the horizon apparently at eye level. No,
yeah, your eyes aren't going to be able to measure that, are they? Let's be honest.
Exactly, and this is exactly the math as you do it on the small scale. But if you enter these big values, you come basically to something which is like we see the world. We don't have to look down at the horizon; we see it at eye level. No.
Great.
And then I got a comment, what is your rate of curvature? Okay, this is not the right term, but they used it.
Yeah.
And why they ask it? Because they know I'm going to calculate it. And I did this in the next slide. And it's fairly easy. If you want I don't know really what the rate was. If they think about the angle alpha when you go a certain way here on Earth, W, and it's just W divided by R is the angle. Now this is the angle you have to use the radian, not degree. No, and so basically it's a very simple formula. If I put in 1 kilometer, I get 0.009 degrees. So very small, not noticeable. Yeah. And the next one is for 2 kilometer, it's 0.018 and so on. Now, so basically it's less than 1 degree. Yeah, for 3 kilometers here. Now, and so even if you walk here around, you don't notice that you are moving on a sphere. No.
Well, and that counteracts what they always say about seeing too far and things like that, isn't it? It's very possible to see kind of distances, and obviously we touched on refraction, which helps seeing longer distances. But when you actually look at those degree figures, they're minuscule. You know, there's no reason why we shouldn't be able to see as far as we see.
And our mind is also made to what we see every day. And thousands of years, it was not necessary to know that the Earth is a sphere. Yeah? So the people had other problems in daily life. No? And so basically they did not care. So it appears to us flat. So why don't assume that it is flat indeed? No? So basically our mind on the small scale, you can work in math and physics as if it's flat. This is basically on the small scale, no problem. It's a very good approximation, and this low degree shows that over 1 kilometer, or if you're working even in a lab below the size, you don't have to account for the curvature of Earth.
Right.
And this is always when they freak out and say, "Oh, approximation, you only assume something." No, if your margin of error is higher, then this would contribute. You don't have to care about it, not because you will not notice. And the other thing, maybe they were thinking of this. Here, if you go 1 kilometer, you have to go down basically by 7.85 centimeters. And this if you go this straight line always along, it becomes more and more. And here, of course, it increases much. And their argumentation is very often, aircrafts would normally fly off here, and they have to follow or actively pitch their nose down in order to follow the curvature of Earth. In the end, we see this is the degree angle. Basically, they have to curve down. No? And the other thing is, why don't they have to do it actively? We have the pressure gradient. Here's high pressure. The farther we go up in the atmosphere, the lower is pressure.
And we'll look at pressure in a lot more detail and atmospheres and stuff and like that when we tackle gravity at some point soon. We can obviously review that as well.
You're right.
So what else did you have there?
Yeah, and then the next one was we showed the slide last time. This was a slide of Shane. Shane is one of the flat earthers, which has a quite big account, and he uses really math, but in a way really to spread false information. And I went really last time I showed this in detail. Don't worry, I don't go in detail right now into this.
No.
But in the end, he uses math in a let me say in a wrong way to deceive people to think.
He plays around with the reality and then makes it into a flat.
And because I see how he calculates. He calculates basically backwards, and uses then certain values in order to reach the result he wants to have. And therefore, I know that he must know that Earth is not flat, because otherwise he cannot do these calculations, most likely. And the main point of him is that our eyes can only see a certain distance, because of net refraction diffraction. What is meant? I have here this image. This is basically the angle. These are two objects, and if you move them closer and closer together, at a certain angle, so one object is here, the other's here, we cannot distinct. Our eyes cannot see two different objects. They smudge here into one. And his argumentation is basically, he's basically, in this point, he's right. An object with this size, basically the separation distance, would become a single dot. We cannot see the details, but his argumentation is beyond. We don't see it anymore, and this is wrong. For example, we can see stars, and stars are far beyond our resolution capability of our eyes, but we see them as dots. Because they are, even they are not very bright. In the night sky, we see them. So this debunks it already. And the funny thing is,
all of this is available on your site as well.
This is right.
So this is the stuff that we looked at last week. What came out of that then?
And then I thought, okay, let's go through it. He calculated it only for one color and for 1 meter 80. So instead of the separation distance or the distance of the object, he put in the size of the person, which is nonsense. And he used also only one pupil opening, and I went now with a pupil opening of 4 millimeters, which is also quite reasonable, normal, and it ranges in reality from 2 to 8.
Maybe Shane's a pirate and he's only got one eye.
Maybe he's one eye, right? And basically, the diffraction distance depends also on the wavelength. And so basically the wavelength and the size of the object. So if this is a person who's 1.80 meter tall, after 500 meter, he wears green shoes. The green light would go away because the shoes are very small. So the shoes would disappear. And at another distance of 3,000 meter, suddenly the shirt will disappear. And in the end, everything will disappear. And it's quite clear that it is not this way. We would.
No,
okay,
I'm
this
pretty
is
certain we would notice if people's bodies were disappearing.
Yeah. And here, okay, this is maybe a bit too big, but we would see it blue, smaller, and red on top, and maybe green. We see only a very glimpse of green at this distance. And farther away, for him, we would not see it. And this is nonsense. And then I did the same one here, basically with the windmills. Then I used exactly his pupil opening and also his wavelengths of 666. So flat Earth is evil. I don't, but ironically, he used it in order to calculate the viewing distance on flat Earth.
Oh no!
And so
maybe it's flat Earth. It's 666.
The
conspiracies just started.
And they don't jump on this for reasons unknown. Otherwise, when we have a 666 in our numbers, they jump directly. We said it's evil.
I think they use it more than we do, though, don't they?
Yeah. And then if we would do this for an object at this size, he uses for the objects. Normally, you should use the object size in this formula, but he uses always 1.80 meter, the size of the person, which this makes no sense. And here, basically, at quite close distance, you would see this wind turbine. Then after 4.7 kilometer, green would fade out. And this is accurate. I basically put down the slider for green color. And then you get this, I think it's called cyan color. So after this distance, we would see it in cyan color. And then if I put also the green green slider down, we end up here in this bluish color after this distance. And then in the end, when I put it more down here, it becomes only the violet light would be available. And here we could see it until 7,000 meters. The horizon, by the way, is already for this height at this size, we would see the horizon. So this is from the size a bit exaggerated, but it gives a quite size. But we are on flat Earth. This is why they are here all in one line.
So Shane is basically Shane is a rainbow pirate. He sees he sees everything like this with his formulas. That's how we would see it, and it would be flat, of course. And you only have one eye. So
and they
rainbow pirate. There you go.
Yeah, and they always say space is gay, but in reality, they have the rainbow color on their flat Earth. I don't care about this. Okay, and one of my followers remembered me here after violet fades out. You see nothing, but for reasons unknown, you see. I said, "Wow, he's right." Okay, we have to add a black bar here until eye level. And so basically this would be a view on flat Earth when for reasons unknown we can not see beyond this distance, but for reasons unknown we can see the sky. And if we could not see the sky, it would like this, but for reason unknown we see the sun. And if we don't see the sun, which would be correct after his thinking, it would be black. And then I thought, okay, I have to
pirates live in the dark.
I have to be fair. We should. He says after this horizons we don't see anything anymore. Okay, we go this. Then it would look like this. Here's your, and then it's black.
You're missing windmills. You're missing windmills.
Directly, they are directly gone. They are directly gone. And here, I can zoom a little bit in now. And here you see basically. yeah, here also the sky's gone. If it also would be the same for the sky, and here, of course, the same like here. And this one is if we would use a realistic realistic optics on flat Earth, it would similar look like this. No? So
just
basically,
blur into nothingness.
the only thing which would limit your sight is the scattering, the Rayleigh scattering of the atmosphere. This makes it quite bluish, and so you would in the distance see the things fade away. And even on clear days, you would never see a sharp horizon because the scattering will limit your view, so you cannot see until infinity.
You'd feel like you're permanently in fog, wouldn't you?
Yeah. So okay. Honestly, I made it a little bit bigger. This is basically how it would like if you look through a telescope or something like this. Now,
Got it.
if you could look in with your naked eyes, the blurriness will be much smaller. And then here I picked the picture basically how it looks in real life now. And you see here the windmills, this especially here, they are already beyond the horizon or below the horizon. And the reason is here's the horizon, and everything which is beyond your line of sight, you don't see. Everything above you see. And therefore the horizon is always sharp because it's basically one line where things leave your line of sight. No?
Absolutely.
Okay.
Conspiracy music's right. He agrees that just the fact that flat Earth would not have horizon proves the globe. You know, that is the one thing that kind of makes me laugh about flat Earth, is always saying that you can't see the curve on the horizon, forgetting the fact that there's horizon there. You know, and we discussed the horizon in last week's episode. Well, 2 weeks ago now, wasn't it? So please have a look at that, and we can obviously go over some more bits and pieces, and we'll get onto motion soon. But this is stuff that was brought up from last week.
Right. Okay, then you prepared a few videos.
I prepared some fun stuff for us. Let's just take that down for you.
Okay.
So we got you can put that to bed for 5 minutes or 2 minutes or however long it's going to be. But this is the classic Dave Weiss one, isn't it? And I wanted to kind of show you that this actually does work in reality. You know?
This is basically how we move through space. The planets are orbiting the sun, and our sun is orbiting the Milky Way. But we have to say, in reality, one circle around the Earth, around the sun of Earth, takes 1 year. So if you would play now, you're playing it in real time. It would be a freeze frame.
and that's what I wanted to show is that what Dave Weiss and others show you is this video in motion. You know, this is very, very nice animation that was created by Mr. DJ Suda, who Dave obviously stole. It's very nice. It shows the moving parts of our little mini solar system there. But the reality of it is that when Dave says, "Oh, you're moving thousands of miles an hour and all this, and you're going this direction, and like, oh, how can it work?" This is what happens in reality. This is how fast it is. You know, it's nearly kind of like a still frame.
Right. Exactly.
So, and that's something to bear in mind next time you see Dave Weiss going on about this. And this is to anyone who doesn't quite understand it. And that's why we're here. It's to sort of show reality. Now, this is the classic movie.
Thank you for showing German service. I'm German. So
well, I think we've kind of got over that now.
We agreed about this video.
You chose it. It's because it's a good film, and it's a comedy. It's all a bit of fun. But this particular scene is very relevant to motion, isn't it? Because it's all to do with reference frame.
Right. It's about the reference frame. Basically, if you start the movie, who who is moving depends always on the view of the observer. So if you are moving,
Sorry,
you
let's do that. I'll just turn that off. Go on.
Okay, you see the reference frame. For him, the train station is moving, and oh hell, it's really moving.
Yeah.
Oh,
And that
okay.
realistically, now, and I put it on it again a little bit slower so people could see. This is essentially us on Earth with the stars moving past us, where you could say that we're the sun and the station is the Earth, and it's all to do a reference frame, isn't it?
Yeah, exactly. So he has to catch the train station now. Okay.
So this is, in my opinion, one of those sort of moments where sort of flat earthers look at the reference frame incorrectly, shall I say? Because obviously they're coming from the angle that we are on a stationary Earth, and therefore it is everything else that is moving around us. Where the galaxy, the solar system, and the universe are all moving with us, and we're moving with it.
Exactly.
So it's a little bit different, but it's just worth bearing that in mind. Now these guys, I'll make this full screen quickly for everyone. These guys just defy what flat earthers would be able to comprehend, maybe, because this is motion in motion.
Yeah. So basically, the reference frame is the train, and the train is moving at a constant speed or velocity.
Well, look, that's the Earth.
And so they basically, if they would not look outside and there would be a wall about, they would not notice that they are moving and the Earth is not moving. Yeah, and it's already not correct to say the Earth is not moving, because both moves relative to each other, and the reference frame itself at a constant speed, is basically for you, it is basically not moving. You don't feel accelerations and so on. The only thing is, because this is on Earth, you will feel the wind resistance. So I think they did it not at very high speed, but if this would be enclosed in a train, you could not say that you are moving. Okay, you will feel it rattling, but if it would not rattle, you would not know that you are moving. No.
But it's showing the whole sort of concept visually of the way that some people sort of believe that if you raise a helicopter, the Earth would just move underneath it if they're rotating.
Yeah,
this is them moving with the actual train. So if you imagine the train being the Earth is moving, they're moving with it because they're on it, and therefore any of their motion that they put onto that, so them accelerating by running or them jumping, are their own individual forces on that, but it's still all working together as one fluid motion, isn't it?
Yeah, exactly.
So I think they're nuts. No matter how fast that train is going, you slip and you fall off a very large.
Yeah. And when you sent me the video, I looked only very short at this, because this looks, it is quite dangerous actually. But if this train would standing, you could do the same.
This is no different to what they do on a basketball court, is it?
Yeah.
This is a basketball court, but a moving basketball court, which shows that the whole relative of motion, and we'll go into motion and perpetual motion in a little bit more detail, but it just shows how to visualize it in a way. I think it's although it's a very good piece of art and a brilliant stunt, it shows the reality of motion with multiple moving things working together, and how they're not impacting each other in the way that they're not flying off the back of the train every time they move.
Yeah, exactly. Because this is what a lot of people think initially, that when you're in a moving train or moving car, if you would jump up, that basically you would go backwards, because the car is driving forward. But this is not the case. You are driving basically in the you're in the same reference frame, and you will not notice it. No? This is why you can run around in a train or an airplane, which is even faster. No?
Now the last one is them guys again, but doing it in a way that is very easy to visualize the fact that they're moving, but you're moving with the earth. So it's a question of sort of whether or not you can understand the concept of the motion that the well, let's watch it and I'll play it. So what we're looking at here is somebody moving with an object
exactly,
in tandem with that object. So
and
you're not going to fly off the earth if you
yeah, and it would look like the same if they do it inside indoors, basically. No? And
yes, you wouldn't feel the motion, is what we're saying. You know, the whole thing of like flat earthers saying, well, why don't we feel it? They don't feel that. How do you do that? You know, that I'll just bring that back, actually. Like when you actually see that of him going up physically flat like that, that
you're not flying flying off. No? You're just going up and down in your reference frame on this trampoline. Yeah.
And this is the thing that sometimes I think that flat earthers try to argue but don't understand about what we were saying originally, that the reference frames are a huge part of understanding the world and the reality that we live in and its surrounding solar system, galaxy, universe, etc. And that is a prime example that, like, something in motion staying in motion, isn't it?
Exactly. Yeah.
So he's already in motion with the actual trampoline being pulled by the tractor. That's a motion of a forward motion, and he's got an upward motion, so he's already in that motion, and it's staying in both those reference frame motions, and that's why he's not flying off the back of that. So it's a good visualization if you ever see anything like this in the future, to sort of try and understand how it relates to what you might hear from a flat earther, because they might say that, like, this doesn't actually relate at all, but it actually shows you that because of different reference frames and different forces working all together, that in our reality it's very easy to have a globe in space that rotates.
Exactly, and the reason why this is counterintuitive is on Earth we have always air resistance, no? And they translate basically the air resistance as if this force would always act on you, no? But it does not when you are in a vacuum, yeah. And only because here the Earth stands still, and they are moving, they feel the air resistance. Okay, then I think I start with the slides. So wait a
yeah. So tech, as you probably gathered, is literally our tech side of the business. I'm here for my handsome good looks and my ugly teeth.
Yeah. So you can see it. Okay, then I shared completely.
I will share that.
Use
there you go.
Laser pointer. Okay. So yeah,
he's already, my folks. Strap in for some education.
So yeah, right. And so what we basically saw is the inertial frame, or the inertial reference frame should be the complete word. And an inertial frame is basically when you're moving at a constant velocity with no acceleration. Yeah, this could be on Earth, basically velocity is 0 or velocity is constant. Inside, it's the same. Yeah. And this is also here regarding the inertial frame, or based to Newton's first law: object keep in motion until a force acts on it. And when we have no force acting on it, we don't feel something inside. And in classical mechanics, so basically the simplest form of the motion formula will work here. We don't have to add for anything in acceleration from outside. No,
which is similar to what we like. The guy who was sat on the train, his reference frame is obviously inside the train, but it shows that the inertial frame of constant velocity with the people on the trampoline is still no affected because there's no actual acceleration in what they're doing while going up and down.
Yeah, exactly. And basically, this is based on Newton's three laws. Today we go completely Newtonian, no general relativity or something like this, because
Einstein will wait. We'll deal with Einstein.
We'll do it other time. No? And here, basically, the first law is inertia. An object stays at rest or moves at a constant velocity.
Just quickly, the Drunk Debunk Show said hello. Well, this is a huge honor. Drunk Debunk Show, if anyone hasn't already subscribed, is a fool or a flirt, because Drunk Debunk Show, brilliant job, fantastic channel, really hitting the numbers as well, getting everything they deserve. So well done to the Drunk Debunk Show.
Okay, great. Yeah, thank you. Yeah, okay. First law is basically inertia. So basically something that moves at a constant velocity unless a force is acted on it. The second law is basically we define the force as mass multiplied by the acceleration. This is our force. No? And the third law is action-reaction. So basically, this is basically when you shoot a gun, the bullet flies in one direction, in the other direction you feel the recoil. And the impulse is the same. Yeah, this is basically action and reaction. We come to this one later. This is basically also how a rocket works. But what we saw now in the video is a linear motion, a linear constant motion. Yeah, we saw in the video first these rotations, but I showed you also on regarding the horizon, regarding scale. It is okay to basically approximate this as a linear motion. Yeah, so basically when we have a linear motion without any acceleration, so the distance traveled will be velocity multiplied by time. No? And here inside you feel nothing, as if you are standing still. No? And so we don't feel it.
We are following you with bated breath here.
Okay.
I might have to put it on full screen, because all I'm doing at the moment is sitting here like a nodding dog, just agreeing with you, because it all makes perfect sense, doesn't it? I'm sure anyone can understand this. So let's make this full screen, because otherwise I'm just getting it.
Okay.
All right.
And the next thing is basically the linear accelerated motion. So basically we have now a velocity, but we step on the throttle and accelerate. No? And the acceleration is now short, will be A, velocity is V. And basically a constant acceleration is velocity by time. So basically it is how much the velocity gets higher over time. No? And when you calculate the velocity, you have to use the original velocity and then acceleration multiplied by time, because the longer you step on the throttle, the faster you go. This is basically what they say. No? Okay. And we feel it. Yeah, everybody who stepped very hard on the throttle on the German Autobahn, you feel it. Yeah. But what do you feel?
I haven't had the luxury yet, but one day, my poor little Seat Leon will probably blow up with me trying to force it over the 130 mark. But
oh yeah, yeah. So basically, what are we doing? We are accelerating forward, right? We are becoming faster. But what do you feel? We don't feel being accelerated forward. What we feel is we are pressed into the seat. Yeah. And this is basically action and reaction, which we had from Newton's third law. Yep. We have this acceleration and our inertia. Basically, our body wants to stay where it is. No?
And where it was, because you moved forward. Yeah.
So basically, you feel an acceleration backwards. You press on the seat, and this is called. It's exactly the same value as A, but only in a different direction. I call it here A inertial, and it's called an inertial acceleration, or when you multiply this with the mass, it is I have it here. Then you have the inertial force. Earlier in literature, they said very often pseudo force, and the flat earthers jump always on this. And this is also a term we don't use anymore, because pseudo force implies that it is not a real force. But when you're in a car and you accelerate, you feel it's a real force. But the difference is, it is not. This one is the reason, and this is only the reaction. Yeah, without this one, you would not have this one. But it's a real force, and because this force does not come from inside this frame of reference, it comes from outside, the car's accelerating, we call it inertial force, because our body wants to stay where it was before. No?
Or you can almost think of it as maybe an initial, because that's your initial position, isn't it?
Yeah.
Right. It's not factually correct, and we are trying to be as factually correct as we possibly can for everyone who's watching. Nikoti seems to think that they would struggle on the autobahn. They think that they would get kicked off because they tend to be driving slow. Is there any rules on the autobahn for driving slow, or is it?
Your car has to be capable to drive at less 60 km/h, but I would not recommend to drive this slow. But the recommended speed is 130, trucks 80, and otherwise look at the sign. Very often you have 100 or something like that.
And that's kilometers, isn't it? Not miles.
Kilometer, not miles. We have here the metric system, and so basically, and it's a loophole that we can drive as fast if we can. There's nothing stated that we're allowed to drive as fast as we can. We have only no limit. It's not forbidden to drive.
And like you say, there are actual parts of the autobahn that are limited to 100.
I think 2/3 are limited. I think less than 1/3 is unlimited, or let me say, there's no restriction, or so basically it. But I recommend
80-ish, isn't it? 80 miles per hour, 100, something like that.
Yeah. So, but I recommend, if you're in Germany, go slowly, it takes years of experience to drive very fast without accidents. No, because you have to drive in a complete different way. You have always to look straight in front, and to look if somebody wants to overtake, and then you have to brake. No, you have to be ready for this.
We have motorways, and anyone who's Audi, BMW, and Mercedes driver is probably quite used to driving at 100 miles per hour on a motorway, but not legally, of course, just because they do.
Yeah, I did a lot of business trips when I was a little bit younger, in my 30s, 40s. I was driving a lot more than 200 km/h. And
you heard it here first.
But I had no accident. But you have to be very careful, and it takes years of experience. Otherwise, you kill yourself. It can become very fast, very dangerous. No?
This is kind of the problem with some people going to the autobahn just to do that, isn't it? Without the experience.
Without any experience. Yeah. Okay.
Right.
And so basically, this is what we saw in your video. No?
Mm-hmm.
And what we did not see is what happens when the train or something would accelerate. Then they would leap backwards. When they leap up, they would fly backwards. No, when you are accelerating. In the next slides, I use always the acceleration, not the force. If it's for you easier, you can always think of this as a force. No, it is physically not the same. So basically, a force is acceleration multiplied by mass, but it basically works the same like a force. No? And
so if you're heavier, will you feel it more?
Yeah. The force is heavier. So basically the force goes
It's your mass,
proportional up
isn't
with the
it?
mass.
Yeah.
Yeah. So basically, your seat will complain. Yeah. If you're heavier, your seat will have to work more than when you're
or you end up
lightweight.
in the back seat, maybe.
Yeah. Right. And so basically, this kind of acceleration we would feel, but here in the motions we saw, which we can basically approximate as linear motions, without acceleration, we won't feel it. But we saw, and this is where the flat earthers jump on, and with this I continue, because they are not completely linear. They are, they are orbits. No? And so now we look at it.
Orbital motion, yeah.
Orbital motions, yeah, and they jump always on it. And now I say, okay, we look at this too. No?
Let's explain that to them. Yeah, let's crack on and explain that one, because we're not afraid to do any of this. And that's the one thing about this channel is we're not going to sit and make fun of anyone. You know, we all have different learning disabilities, and I call them all disabilities because we all have learning disabilities, whatever it may be. And this is our way of sort of trying to explain reality in a semi-fun but educational way, so that you can actually see it and understand it in a little bit more realistic way, rather than somebody saying, oh, that's not possible, this isn't possible, and having a big argument. Because although some debates are fun to watch, they don't necessarily teach you if you're already stagnant on one position. So this is to try and help people understand why sometimes somebody from a reality follower, as I call them, rather than a globie. So a reality follower might actually try and explain this in a debate, but obviously it's quite difficult and in depth, where we're trying to do it so that you can just look at this in your own time. And on that, I'll let you get on to motion.
Okay, we have here, as we had before, a linear motion. Now, so M stands for the mass. This is an object, and this arrow indicates the velocity. This one is moving in a linear way. You won't feel anything. It's basically inertial reference frame. No? And now we're doing the following. We add an acceleration or force perpendicular to the velocity. Now, so what is the and we ensure that this is always perpendicular. Now, this is basically the rule number one. What will happen? The object still wants to go into this direction, but this acceleration would pull it down. Yeah, with basically also. Okay, this is a vector. Now, with the same one, with also an arrow with a V down here. No? But obviously, this object cannot move in two directions at the same time. What happens? It makes a compromise.
Unless it's been drinking, because I find I can move in all sorts of directions.
Then you see two. But in the end, this direction and this direction will basically overlap, and this object will fly basically in this direction. Yeah. But our rule was this should be always perpendicular. So what happens? This is the new vector. This object has moved down here. And this was the one which is now diagonal. No? And we have the rule, it is still a perpendicular. No? And so the next motion would be here in this direction. No? This would be in this direction. And basically this force or this acceleration is dragging the thing around. Yeah? And because it is not only going in this direction, because it wants also to go in this direction. And therefore, basically it makes a compromise and goes like this. And maybe you guessed it, it goes like this, and you have a circle. Yeah. And this is the interesting thing, a constant rotation. So this stays constant.
And just to be clear, that we're looking at the is this where the velocity and the acceleration are equal?
No, they are not equal. This is they are different. Now these both have nothing to do. This one is only perpendicular. No, it can be stronger or less. No, and depending on the strength of A, basically the radius of your circle will shrink.
That's what I wanted to clarify.
Yeah, exactly. It will shrink or become bigger. No, and we call this, when we have a constant rotation, we call this velocity the tangential velocity, because it is tangent to this circle. No?
Now that's tangential to our American viewers, but I'm the one with the accent between the two of us.
Okay, my German accent is coming through the longer I speak.
Europe, so the majority of Europe understand you better than they understand me, so I wouldn't worry about it.
Okay, okay, great. Okay, and if you've ever been on a carousel, you will feel a force outwards, not inwards. What
That's
you
scary.
feel outwards is the inertial force. It has the same value than this one, but to the opposite direction. And this is the centrifugal force which we feel. And but responsible for this is the centripetal force, and this is A. The centripetal force is basically the force or the acceleration which points to the center. And this is basically the chain which is fixed on the carousel. This one makes basically the force that this is not flying off. So the feeling is you are pushed outside, but in reality you are pulled inside by this thing, and you're not pulled completely inside because you're rotating. So basically this driving in this direction prevents you from crashing into it. And so if you have maybe here a rope and a ball, and you swirl it around you, you feel really in your hand that you have to apply a force to stop this ball from flying off.
Hold on. We got to see that demonstration again there, Tech, because that was beautiful to watch. There you go. So the ball above the head, let's have a look at it again, because I'm pretty certain that
the rotation.
Yeah.
Wait, so opposite. Okay. Okay, this was basically
you're spinning. Everybody do a do-si-do and spin a ball around your head, is what we're saying.
This is basically, now we look at it this way. In the center, you're standing, you have a rope, and here a ball. And when you spin, you really feel that you have to pull it inwards, otherwise this will fly away. And this is basically what we do. But if we are this mass, we would feel this, the inertial force. And now the interesting question is, what happens when we cut the rope? Does it fly here in the direction of the acceleration, or in this one?
Oh, well, I mean, there's few people watching too. Who has the answer?
Spoiler, it will fly. It will fly in a showed the direction, but it flies in a straight line, not in a spiral line or so, because no force is applied anymore, and it becomes again an inertial system flying only in straight direction. But if we cut the rope, this disappears, and when this disappears too, and only this one will remain. So it will fly off tangential in a straight line. It does not fly in this direction, because this is originally, when I started to make the slide, the thing in which I thought, because you have here a force, you feel the centrifugal force, but it directly disappears, because but this is the reason why we have this. And with this reason disappearing, this disappears too, and only inertia takes over, and you fly off in this direction, not perpendicular, tangential. You fly in a straight line.
It goes against how you would think it would happen, doesn't it? But in reality, That's the truth. Once you get rid of the AI disappears automatically because they're just working against each other, and the only thing left is your velocity, which is moving in a straight line.
Yeah, and this is the interesting thing. Sometimes you have let me say, the feeling, basically what is plausible to your experience, no? And you feel a force and you think, oh, it's flying off. But if you look at this, what happens in physics, no, in mathematics, you get the understanding, no, this goes away, then this has also to go away, and inertia takes over. And the inertia is in this direction. And we have this on the carousel, and otherwise we have it also in the solar system. These are the orbits around the sun. And here, basically, the centripetal force is gravity. And gravity goes in this direction, but orbits are a little bit special because gravity we look at today only in Newtonian way. At the end, we make it a small teaser to general relativity. But in this one, basically, gravity is not pulling on a certain side. It's pulling on all molecules, all atoms of us. So the acceleration would be in this direction, but we fly fast enough to not crash into it, and we fly basically so fast that its centripetal acceleration is the same like this, so we don't feel anything. So basically, if we would feel weightless, okay, we have the gravity of Earth, of course, but we don't feel basically the influence of this gravity, because we are flying. We basically these both forces are canceling out here in this case.
Yeah. Now, obviously, Tech's using the word flying, but that's just
orbiting is the correct word.
He's translating while doing this. Remember,
translating,
So he's tech translating while doing it. So do apologize if anyone thinks that we're talking about flying in the way that a bird or a plane flies, because this is orbital dynamics, isn't it?
Yeah, right. And here, this circular motion, a constant rotation, we can feel. Now, this is, or I wrote, we can calculate it, because we'll later see how big it really is. And I forgot this. And the interesting thing, a constant rotation is a constant accelerated motion. And the thing is, the acceleration is perpendicular to the velocity.
Yeah, and they're equaling each other out, which is how the orbit remains constant, isn't it? So
exactly.
So go on.
So please ignore the math for a while. Look at this one. This is one of the memes in different variations. So Earth is spinning when you look from the north counterclockwise. And they always say the Earth is spinning at 1,650 kilometers per hour. Now, this is damn fast. No? Obviously, I think in next to the surface, the speed of sound is about 1,300 kilometers per hour. Wow, it's supersonic, right? And this sounds very fast, but the Earth radius
very
is
big ball, isn't it?
It's a very big ball, and what they don't understand also, it depends where you're standing on. If you
this is important to kind of like realize that, and some people have obviously explained, I'm sure, that the Earth rotates 15 degrees per hour, or half the speed of a hour hand on an 24-hour clock.
So
but realistically, that this is the sort of like the numbers that are brought out to scare you, aren't they? The 1,000 miles an hour here, and we're moving through space at this huge velocity. But it's all to do with what we're talking about. That it's in relation to your reference frame of where you are. Now, you're already moving at that 1,025 miles per hour. Just by sitting here in this chair, I'm already moving at that speed. But because of what we explained with the not feeling that constant motion,
Mm.
Everything
Yeah.
around me is moving with that. So it's a constant motion that's not affected. It's not accelerating. It's not having any
Mm.
form of inertia because it's already in a constant inertia reference frame anyway.
Mm.
So that reference frame is that constant. And
Mm.
that is
It's
why
mm.
this ball could spin as fast as it likes. You
Yeah.
know,
And
in reality. We would be
yeah,
removing because we would be moving with it.
at
I
a
mean,
certain
if it was
speed, we
moving
would really
faster,
fly off.
our,
But
our, our day and night would be a bit different, and we'd probably need a little more
yeah,
gravity to hold us on.
yeah,
But
yeah.
the theory can be upscaled to any particular speed, though, and you shouldn't be scared of.
A
It's
little.
going to tell me off.
Okay.
It
So
almost. You know, the point
almost,
is, you
yeah.
shouldn't be scared of big numbers. You know,
You
just because
can
you hear this doesn't mean that it's not explainable.
theoretically you can spin the Earth also that you fly off, no? But not at the speed. But we will look at this later.
We could have some
Here,
more gravity, though, couldn't we?
yeah,
And then
yeah,
if it's
yeah.
bigger,
Then
we could have a bit more gravity, and then
exactly. Yeah,
we might look a bit different because we'd be a bit hunched over and sort of
yeah,
squashed a bit more. But
yeah.
otherwise, the theory is
And
there.
so
But
if you're standing at the North Pole, you would turn on your own axis once in 24 hours, very slow. So, but your tangential velocity would be 0. If you
mhm.
go down, also the distance to the axis of rotation becomes bigger and bigger. This is here the radius, and we will see how it impacts the speed. And from there we go. So this is one of the. So basically, we come back here to the image which we had. Now this is the radius. This is the tangential velocity, inertial force, and sorry, acceleration, centripetal acceleration, and so on. And
You're okay, Nikoti.
yeah, I'm
We're
okay.
not going to make it go any faster for you.
Yeah.
We'll stay at the speed. I mean, if it goes slower,
Mm,
that could also cause problems as well. We're actually at a
okay.
pretty
Yeah.
perfect speed.
So we have a constant rotation, and I said it already. A constant is the constant accelerated motion. So you feel something. There's something you can measure or calculate. And we said here we had this speed at 1,600 something. But when you say your engine, the rotation of your engine, you never say it in miles per hour and kilometer per hour. You always say RPM, so rounds per minute, no? And basically
Or
Earth
revolutions
do,
per minute,
yeah, and
depending on
Earth
your
do,
location.
and Earth do one revolution every 24 hours, no? And this is basically, in math, we rather use angular velocity, but it is a similar thing like rotation period. And this one is constant in this case. And don't be scared for this. This is an omega. This is just letter like the others, but a lot
Boobies.
of people, yeah, oh, yeah, or something else, yeah. But, oh, I put this away. And,
You can tell I'm a child, can't you?
yeah. Yeah, and so this is an omega Greek letter. I don't know why Greek letters used, but this omega is basically the angle over time. Yeah, so this is basically how we measure a speed. If you would reverse this, time divided by angle, you have your rotation period, your RPM. No? But we do it here otherwise in the other direction. And for Earth, we do 360-degree turn in 24 hours. This only is omega, nothing other, nothing worse. Yeah? And so this is basically the angular velocity of Earth. And in math and physics, we like not to use degree, we use radian. So instead of 360, this would be 2 pi. The beauty of this is if you have this one and you multiply it by the radius, you get already, this would be 2 pi r, and then you have directly the length. Now, this is why we rather use this one. So the tangential velocity is constant, as we said this, but the direction constantly changes. No?
Yep.
And we can calculate the tangential velocity by multiplying it with the radius. with the radius, we have, when we have this, and we multiply it with the radius, we have this velocity. And vice
It's hard
versa.
to concentrate when you're
Yeah.
pointing and laser pointing at boobies all the time. But
Sorry, yeah. So I marked here red the important formulas where you look at the others. If it's too much, you don't have to look so much. So and the centripetal acceleration is also constant. So this one is constant, and it's always pointing to the center. And we can calculate this too. And this is sorry, I renamed it here. R centripetal is the angular velocity squared. So basically angular omega multiplied by omega, and mal r is this velocity. Yeah. And you can write it also in this way when you replace the omega by this one. No? But the most important thing is this one. And you see this force or this acceleration, yeah, depends on the radius and omega, the angular velocity. Yeah? And you see this is squared. This means if you have the double radius, this force or acceleration will be double strong. If you double the angular velocity, it would be 4 times strong because this is squared. Yeah. So the rotation speed or angular velocity has a much higher impact than the radius. No?
Yeah.
And we already saw the Earth is rotating very slow. And today I looked how this is calculated, and it was, don't worry, I don't walk you through it, but I did this today because I wanted to understand it. And I had this somewhere in university, but I did not remember it. But it's correct. I verified it.
Then this, folks, is what tech does for a bit of fun.
Yeah.
Okay.
Right.
To me, this is all like a lot of complicated stuff. You know. But as he just said, I wanted to find out what it was, so I just did all this. And this is why tech is here. You know, I can kind of tell you that things rotate and things move. Tech can actually explain why. You know, this is the reality that we're showing you here.
Yeah, and when you look, it up, you find it. You find a lot of explanation how it's done. So everybody in the end, who knows a bit of math, can verify it. Now, so it's not secret because this is what the flat earthers say. They say this is made up. Yeah, and on the one hand, you can measure it. You can measure the strength, and you will see the impact that it works out. On the other hand, it's not secret. You find it in every textbook how it is done, and you can verify it. Okay, you have to know a little bit of math, but it is verifiable, no? And these things are not made up. No, this is always their claim. No, okay,
absolutely, and this is kind of why we're doing this, isn't it? Is to show those flat earthers who may be a little bit. I wouldn't say unsure, you know, because like I say to you earlier, I don't like to say that somebody
it's counterintuitive.
Yeah, exactly. All this
counterintuitive. No?
Yeah, and sometimes you need to sort of see that this has already been looked at in great detail, you know, and we go into great detail to show you the great detail.
They always say also we in university or in a school are going to indoctrinated. No? And I tell you, especially in university, I met people much more intelligent than I. And if they would make up something like this, they would have found it out already. And the other thing is, it is everything like this. It's open. It's basically open source. Yeah, it is not a secret. You can verify it. Of course, you have to have a little bit knowledge of math. But it's like repairing a car. A car is also not magic. I cannot do it. I'm not a car mechanic. I can do very simple things. Refill the water for the wipers.
change the oil and fill up the water.
No, changing the oil I would not do.
Okay. Well, I'm better at you at one thing.
I'm on the theoretical side. So,
I can
it's
do the
basically-
mechanics for you, but you can tell me, explain to me why there's a velocity and a viscosity of different oils.
Yeah, about fluid dynamics, I don't know so much. Classical mechanics is more my thing. And in the end, like repairing a car. For me, they are doing magic. Yeah, but I'm sure they know what they are doing and they learned it. I hope so. And here it's basically the same. The car mechanics, the mechanics like me, we do know how to do this. It's written down. Everybody who can look into it can verify it, and it's not an indoctrination. Everything is broken down to the smallest elements and verifiable. No, and it's not always.
I think somebody's got on the wrong show. Hello, West Side Girl Reacts. Hello, fitness friends. You haven't seen me, have you? Because I'm not very fit. But welcome. I hope you're enjoying this.
And now we come back to the first slide as the video of the spinning Earth and so on, and to get a feeling of why we can also approximate a rotation motion basically as a linear motion is this is basically our galaxy, how we think, or basically according to the latest knowledge. Now, we cannot see our galaxy from outside, obviously. We looking here. Everyone who saw the Milky Way was either looking on the sky, either you was looking in this direction or in this direction. Basically, this is the band we see over our head, the Milky Way band, basically. This is basically a part of this arm. Or of this arm, in which direction, depends on which direction you're looking. And with radio telescopes, infrared telescopes, we are quite sure that our galaxy looks like this. But 100% we don't know. And the estimation is basically that the size is about 90 to 120 light years. This means the light needs about 100,000 years to go from here to here. So it's enormous big, no? And our sun is estimated to be basically, I know when 10, 20 years ago, it was thought that we are more on this side, but now we know that we are a little bit more inside. And a full rotation takes now I've counted zeros, 240 million years. One rotation.
240 million, yeah, I can count.
40, yeah. So if we round this up to 250, in 1 billion years, basically we fly around 4 times, no? And Earth is estimated to be 4 billion years old. So basically, Earth orbited already 16 times this way. Now, this is quite amazing. And but for us, everything seems static. It looks as if it's standing still. No?
Yeah, because this is huge, isn't it? And like you say, just like that rotation there, a full rotation is 240 million years. So
exactly.
none of us are going to experience any real change in what we see in the stars above us. You know, there are some stars that have moved over 1,000 years, even some that have moved in hundreds of years. But in reality, you're not going to suddenly wake up tomorrow and find a whole new solar system outside your window, because it's going to be daytime for a start. But if you wake up at night, maybe that'll work. But it takes such a long time for things to actually move because it's so huge. Our reference frame, which is what we're kind of looking at with motion, means that a star that you look at today is going to be there for your grandkids in pretty much identically the same space. So you're not ever going to see it move, but it does because we're doing this over a very, very long time.
And further, the stars are all moving in this direction. So basically, this means this make the movement even slower. Now, there are shifts in the constellations, as you said. Some are over thousands of years. Yeah, today we have measurements which can measure over decades a very small change. No, and if we estimate this, you would with your naked eye see in 1,000 years maybe a change. There are a few exceptions. There are a few stars which move already in a decade. You can, but I'm not sure if you can see it with the naked eyes, because some stars are very dim. But there are a few stars where they showed photos 20 years ago, 10 years ago, and you see them slightly moving. No? So what we
So
see
is that because they're closer than the other stars that we
you
normally
have
see?
gravitational interaction between these stars here, no? Also, so they are not all moving uniformly in one direction. There's also movement in between. Yeah, and but this movement is very slow compared to this movement. So basically, yeah, in our lifetime we see everything moving with us, basically, and then in shifts. We are not the only one moving. Here's our Sagittarius A. This is the black hole, supermassive black hole. Nearly every galaxy has this. This is also quite new knowledge. I think it's 20 years or something like this, 20 or 30 years that we know this.
Not very long. But
Because,
that's where we're developing, isn't it? And like being able to like see more into space, and our technology is getting to a stage where we're actually able to find out new things, and even things that we don't understand. And it's having this sort of knowledge from this basics about how things will work together is helping us actually unravel some of these newer mysteries, isn't it?
Yeah, and all spiral, basically also Andromeda, our next galaxy. Most galaxies are spiral galaxies, and they all have basically a supermassive black hole. And it's quite, we don't know where it comes from. Maybe it's the remnants from the Big Bang, or it formed directly after the Big Bang. We don't know this 100%. No? And this is, the research is going in this direction. And yeah, James Webb Telescope made discoveries. Now they saw galaxies very early on in the birth of the universe, where we thought there would be no stars at this time. So our entire model have to change within the next years, and it's very interesting. Now we discover new
we're
things.
learning again, aren't we? We're learning more things. I mean, it'll all fall in place, but it is interesting to find stars that are potentially earlier than when we thought the initial Big Bang was.
Yeah. Not the Big Bang, but after the Big Bang, we thought a little bit, it would take a little bit more time. But
we're getting closer to the Big Bang, then, aren't we? By finding these things, we're getting closer and closer. We'll never get there, because I don't think we'll ever. Personally, I don't think we'll ever be able to get that ability to see that far in the past.
The reason is, the farther we see, the light takes a long time to go from here to here, and the farther you look in the distance, the farther you look in the past, because this light came already here. When we would look here, this light of a star would have taken 100,000 years to come to us. So basically, we see how the star looked 100,000 years ago. And in the same way as when you look to other galaxies, which are billions of light years away, we're looking billions of years in the past, basically. No? And this is basically how we can, with bigger telescope, look more and more into the past. No? And,
we'll get there one day. It's not in my lifetime anyway. So the satellite's falling to Earth near Nakoti. That's obviously a little bit of a worry for the poor guy. They're just coming out of their orbital rotation, because all satellites are falling, aren't they? Just a lot of them break up in the atmosphere as they fall out of the sky. But And some
Yeah, you have-
malfunction and just have a glitch and fall out of the sky. But the Kogi seems to be collecting them by the sounds of things.
Yeah, exactly. And so basically, this was the video which you showed. You showed the sun moving through the galaxy and the Earth spinning around. We clarified that this in real time. I'm playing it now in real time. The sun takes 1 year to circle around, and
The Earth
when
takes
we
a year
yeah
to circle around
1 year the sun
Yeah.
sorry. And when we do the math, okay, these are all the motions basically we have on Earth. We have once the rotation, the tangential velocity, and then we have the tangential velocity around the sun. This is 107,000 kilometer per hour.
Mhm.
And then the sun's tangential velocity around the galaxy, which is 700,000 kilometer per hour. No?
And again,
But
don't worry about these big numbers. These are huge
Yeah.
distances, so they're going to travel at huge speeds.
and this is a tiny fraction of light speed, by the way. No?
Yeah.
And so basically, this sounds much, but the way we saw omega, so basically the rotation speed goes
Mhm.
in squared. No? And the rotation speed is extremely small. And what makes it this big is basically the radius. No? But the rotation speed is very slow. And the most impact has the rotational speed. And if we calculate the acceleration, the centripetal acceleration in relation to Earth's gravity. No? Earth's gravity, so basically the force which is, or the acceleration which is putting us down in the seat, is 9.81 meters per second squared. And if we compare this resulting in percent, the rotation of Earth at the equator, because there you are moving fastest, is only 0.34% of this. So minuscule.
Doesn't sound like that's too
Yeah.
bad after all, does it?
And
all
this
these
is-
scary numbers, but
Yeah,
actually hardly moving at all.
Yeah, one period in 24 hours. At the equator, you have this velocity, more than 1,600. And you get this small when you calculate with the formulas I showed later. It's this small percentage of G. So basically, you will not fly off the equator. Definitely not.
No,
There's enough.
I'll be all right. I'll be all right.
Yeah. And around the sun, you feel it is also here in this relation 0.06% of Earth's gravity.
So the Earth isn't going to feel too much effect by being moved around the sun like that, is it?
Yeah, and this is sun is so big, gravity of sun is very strong, but at the position where we are, this fraction of Earth's gravity has basically here the gravitational pull of the sun. It's very little. And when we see the small number, we would think, wow, we would fly away. No, the radius is so big because of this, because this gravitational pull is very, very small. The radius is so big because Earth is flying quite fast around the sun. If the sun would go away, we would fly off in relation to the former position of the sun with this speed. No? But
that would be quite scary.
And this and this minuscule gravity is enough to keep us around a very big radius around the sun. It's 8 light seconds. So the light from 8 light minutes. Sorry, from the light from the sun needs 8 minutes to reach Earth. So
and just so people understand that if we started off with the very basics of this, and all of this is relevant to what we were explaining previously, wasn't it? About the A, the B, and the AI that we looked at earlier.
Yeah.
So
exactly. So basically, and then the rotation around the galaxy. This is really, I don't count the numbers yet. No, percent of this one. So basically, very
I'm not
minuscule.
gonna make you read those zeros. No.
No, yeah. And so basically, even if you could feel these forces, they would be very small. But especially these two, you don't feel because it's an equilibrium. This is the gravitational force, and we feel the inertial force in the other direction, the centrifugal. No? And they cancel each other out. So basically, we feel nothing because of them. No? So even this we would not feel. This is only the pull inwards, and we feel, and it's in equilibrium with the centrifugal force. And yeah, here I did the math.
Of course you did. Tech's gonna do the math for you.
So when I posted this, I posted this directly in the thread, so everybody can follow. And these are exactly the same formulas which I used for the small the example which I showed. No, but I put here in these incredible big numbers, and in order to follow it, it's I converted always in the base units of the metric units, then you can multiply them very easily. And Earth radius, I made meters out of this. So basically, this point basically moves here. And also the rotation, 24 hours are so many seconds. This is a full rotation by 24 hours. And if you put these values in, you get this as the acceleration. And here I calculated how much is the fraction of g, Earth's gravitation. And you see also for the sun, here I had to put in 150 million kilometer. Yeah. So okay. And these are 150 billion meters. No. And here 165 days. I had to convert in seconds.
I swear you just wanted to make life harder for yourself by converting.
It's just easier to, because then I have to type. I did this with Excel, of course. Now then I have to type this in, and I don't have to convert units. And it's less a point of failure. No? And then if you put the values here, you get this value, and comparing it with Earth's gravity, you get this value. No magic, just in the formula which we already used, and which we can also use in the small scale. They work perfectly in the large scale, but for us it is difficult. We're living in small scale world daily, and to put such big numbers in and see only such little coming out seems, first of all, counterintuitive. No? And here's the same with the Milky Way. And here you see this incredible small acceleration which comes out.
Read those numbers then. How many meters is that?
I don't even try to count them.
Being cruel. But this just shows in reality that it's just scalable, isn't it? You know, we've gone from cars to merry-go-rounds essentially, and it's the same theory behind all of them.
It's the same mechanics basically which work behind it. You only put in bigger numbers, and you see these two. So the rotation around the sun, the rotation around the Milky Way, these are orbits. Now I said already there is a centrifugal force and centripetal force in equilibrium. In an orbit, we don't feel anything. But this one, there is really something. We are rotating. The Earth is rotating. So basically, this one really exists and should be measurable. And this is one of the next memes which we see already, which is directly related. 6 km/h in a carousel. He looks scared. 100. This cannot be 100. This shows already that flat earthers have no clue about how fast something really is, because it is maybe 10 or 20 km/h, but not 100.
We looked at this previously, didn't we, Tech? And 100 kilometers rotational like that would you would definitely have that look on your face if you had a face left. To be honest, the G alone would.
And their argument is basically then 1670. Everybody's relaxed, no? And I calculated how much the centrifugal forces the same value, only in different direction, with 6 km/h. When I calculate this, I use the same formulas which I showed before. We would come to this one. This is 2.78. Yeah, if you remember Earth, the acceleration of Earth's rotation, the centrifugal acceleration was lower, and this is already higher. So 6 km/h at this small radius, 1 meter, is already higher. No, so this would be basically 0.28 g. So basically, this fraction of Earth gravitation.
A little bit over a quarter of 1 g.
Yeah. So basically, definitely feelable. You would feel it. Yeah. Whoever I get dizzy in this thing. I hate these things. Yeah. Already as a child. But if you sit here in this, you really feel the centrifugal force. No. And when you see this thing is spinning with, oh gosh, I did not calculate here the omega, but the omega is quite high. It spins, I don't know, a few times a minute. Yeah, and
the revolution is going to be quite high, aren't they?
The revolution is quite high, and as I showed, where is it? Here's the formula. This goes in squared, so this turns much faster than the rotation of the Earth, and this goes in squared, and the radius only multiplied, so linear. So already this squared makes this faster rotation stronger, basically, than the force at the equator due Earth's rotation. Yeah. And it's the same formula which I used below, but when you look at this formula with the square says it, basically the thing which rules it is the omega. Now, and the same is basically with this one. If we go with this 100 km/h, then we would come to 7.87 g. And this is a little bit too high because this is basically, jet fighter pilots are trained in a centrifuge, like this centrifuge with these values, but I think not children.
I'm pretty certain that NASA aren't using children for centrifugal tests.
Maybe.
You know, maybe there's like early. Maybe those fairground rides were actually built by NASA to see who survives. 7.87 g. No. Let's stick to reality, please. Go on, Tech.
If you survive this one, it's a
silly number. It's a silly number, and
this shows already that these flat earthers or whoever made this meme have not a feeling for velocity, and if you put this high velocity, as I said, you never say my engine the revolution of my engine rotates with 1 centimeter from the middle of the shaft with this and this km/h. You always say revolution per hour, and here you have 1 revolution in 24 hours. No? And as I said, this goes squared in here. This value is very low. The radius is quite high, and but this does not counteract this square. No? So in the end, we come here to this 0.0035 g, which is basically what the Earth rotation at the equator. No, the strong is because here you are fastest. What you would feel here, and this is so low. The Earth's gravity is not uniform. We have small variations. So I really doubt if you can really measure it, because it depends when you are very dense ground. For example, iron is you have a lot of iron beneath you, and then you have a much stronger gravity, not much, but a little bit more stronger gravity than when you are, let me say here, on the seaside or something, or on the sea. No? And NASA measured already the gravitational distribution. It is not uniform. It is minuscule different. And I think this would basically maybe not measurable, and it would be the not uniform gravitation would basically hide this one, so that you won't see it. But in the end, over the million of years, even if this is very small, and as you saw, a force is mass multiplied by acceleration, it had an impact. The radius at the equator is a little bit, I don't know, I really don't remember how much, but it's not that much bigger than the polar radius.
And we have to remember as well that we're not actually
Yeah.
experiencing an
Yeah.
acceleration in the same example that you did with
Mm.
the car. The Earth
Yeah.
is moving constantly and has done
Yeah.
since it sort of
Yeah.
formed in this way. And obviously our atmosphere is moving with it because it formed with it
Yeah.
as it was rotating.
Exactly.
So this is something that, like, when you're born onto it and it's already in motion, because you're in motion when you're born, everything that's on Earth is in motion. Our atmosphere is already in motion. So when you are born into it, you're not going to suddenly start accelerating, are you? You're already at that stage where you've reached that speed. Dependent, again, like you say, about the fact that there are different speeds depending on where you are on the Earth in a revolution's
Yeah,
time.
exactly. So basically, Earth formed 4 billion years ago out of dust and rock and a cloud, basically, which was slowly rotating. Yeah, and like an ice skater, if you rotate with your arms extended, you rotate slowly. But if you put your arms to your body, you rotate very fast. No, and this basically happened when the dust cloud contracted by gravity to a planet. No? So we have this one revolution every 24 hours, and I think I read something in 4 billion years ago. They think it was double as fast. No, it slowed down. No, through inner friction. Yeah, so. So it slowed down. No? And as we already said, the scale of Earth is so big. You remember the horizon thing, which you look down only a 400th of a degree if you look from here to here. And so basically you can assume, approximate it as a linear motion, basically. Yeah, and the atmosphere has no problem with following a linear motion, which it already has. Yes, we have also winds, the impact on this, and this is also very interesting. And I think this.
And we're going to look at some of the motions that are affected by gravity when we tackle gravity, and we're going to tackle it in a kind of mature way. We're not going to sit here and try and debunk it in any way, because obviously it can't be debunked. It's a scientific theory, not an idea. And if you need to know the difference of that, then Google's there, or hang around for our gravity special, where we'll have a look at that, and we'll have a look at how tides are affected by gravity, how the moon affects it as well, the tides, and the moon's gravity relationship with Earth as well. I think we can look at that, don't you, Tech?
Yes, this we can also look at another time. Yeah, sure.
So let's tackle the spinning ball, water flying off, the tennis ball, the every other meme that came out of Flat Earth this week.
Exactly. And this is also one of the slides which I made early on last year. I started basically with my account last year, and this was one of the first one in the first month, I think. And here basically this I showed already. I will not go through everything, but here I calculated the how much is the centripetal acceleration and subtracted it from Earth's gravitational acceleration, and then you get that here Earth at the equator, it would be, you would feel still 99.66% of Earth gravity. So basically not noticeable now. And this is the main point of it. And as you say, they always show this wet spinning tennis ball where the water flies off. But the tennis ball turns about, let me say, 2 or 3 times per second or more, but Earth turns only once every 24 hours. So this is basically
And of
difference.
course, they're missing the biggest part of their problem with that meme as well. Is the reason the water falls on the floor is because of gravity, which they say doesn't exist. So it's all very well showing that meme, but you're basically just proving 2 things. You're proving like rotation and you're proving gravity. So carry on.
Yeah. Okay. So I hope everybody was with us with the
I think we did it. Yeah.
And another thing they very often say is Coriolis force. Yeah, we should feel it. And first of all, I clarify what Coriolis force is. But this is basically, they say when a plane flies north and to west, or when you're walking north to west, if Earth was rotating, you have to lean to one side. Yeah, otherwise you cannot go to the other direction. No, partly it's a misunderstanding, completely misunderstanding of the Coriolis force, but it is also a misunderstanding how a force which is small works over long distances. But because we know, I showed later, the let me say the clouds, or how's it called, the winds, how they move on Earth, they follow basically the Coriolis force, and they say this can't be the Coriolis force because it does not work when I drive in a car or in a train and drive north-south. I don't feel anything. Yeah, and this is their argument. Now, so why Earth is stationary? So now we are stationary, and this is, we simplify it. We don't look at it on a sphere for now because this becomes really complicated with Coriolis force. And so we are on a disk, on a carousel, yeah, on a disk, stationary on flat Earth. Hey, so, and we want to walk this dotted line with the speed.
And just to clarify, this is our flat Earth example.
No. It will become later Earth, but we look now on the North Pole basically in 1 kilometer, and we can approximate this at flat.
So we got a flat carousel to look at.
Yeah, flat carousel basically. And if it's stationary, if you want to walk with a constant speed into this direction, you basically have a constant velocity, VR, so V radial or something like this.
Just quickly, Dakota, thank you very much for being here and taking care of things, and no problem at all. Hopefully we can do another one soon and have you along, but thank you very much for being here. You take care too.
Yes. Thank you too.
Thank you.
Okay. So basically, this is the dotted line, and you just want to walk here down this line with a constant velocity VR. And as we learned, constant velocity, you won't feel anything, or you're driving or something else. No? When you go in this direction, you won't feel anything. You are not rotating. You can follow this line. Now we look at the same, but now we rotate this disk. And we have the same goal. We want to follow this dotted line. Of course, this dotted line will move. No? But this dotted line is printed basically on the disk, and we try to follow. And what will happen? We have now a tangential velocity when we start here. This is from the outer rim here of this disk. This is the tangential velocity. If we go inwards, we have the smaller radius. No? The tangential velocity becomes smaller. So basically, when we go from this direction here, we have to decrease the tangential velocity. Yeah,
That would
in
be
order
where
to
that would be the
follow.
point where I would stand on that merry-go-round. You
Yeah.
know, the charged merry-go-round. I would always stand right in the middle because then
Mm.
you get less dizzy and less likely to fall off.
Yeah,
Because
exactly.
of these reasons.
And if you want to follow this straight dotted line on the carousel, you have to decrease basically this speed. What do you have to do? You have to lean basically to the left side. Otherwise, you would miss it. Otherwise, if you would only go straight with closed eyes and only follow inertia, you would basically go this way. No?
And that's because of your mass, isn't it, in this equation?
Yeah. Am I right?
Mm.
You slow. Oh, okay. But you, in order to compensate it, you have to lean to the other side. No? So in order to follow this line and not to deviate, you have to lean to this side. And with this acceleration, you are making your velocity smaller. No? And because you have to accelerate in this direction, axio, reaxio, you will feel this as if there is a force you have to walk against. No? And this is the Coriolis force. No? And the interesting thing is about the Coriolis force, it's only present when you're moving. As soon as you stand still, you don't feel it anymore. As soon as you start moving again, you have to lean to the side. Yeah, and you have to decrease your tangential velocity. And this is only present when you move. When you don't move, you don't feel it. This is also an inertial force, yeah, because it doesn't come from the system. It comes because the thing is spinning. And this is basically, in this direction you have to lean, and this is basically what you feel as the pushing force. And this is how it's calculated, and in it is also the rotational, the rotational speed, or rather the angular speed, and your speed you're moving. And you see, when you're not moving, this becomes zero. This force becomes zero, or this acceleration becomes zero. No?
I think if a lot of this is why people don't necessarily understand the Coriolis and its effect, because there's a lot going on here, isn't there? And
rotational
is go on.
Yeah, rotational motion are very complicated. Yeah, this is not intuitive, no, because it's not intuitive if you want to follow a straight line that you have to lean to the other side. But if you see, basically, you have to reduce this amount of speed. It becomes obvious that you have to lean in one direction. No. And by coincidence, I saw yesterday a documentation of a sniper, and so my binge watching of YouTube every night before I go to bed, and he said how they calculate when they shoot over more than 1 mile, 1 kilometer, what they have to account for the wind, the drop of the air temperature, everything. And then he said, and of course, when we shoot north-south, we have to account for the Coriolis force. And then I woke up. I said, what? And then I said, okay, I have to calculate this, if this is true, because I heard already rumors that this is not true, but this was obviously a real sniper, a professional, and he said this. So I thought, okay, let's look into it. And now we assume we are looking on the North Pole.
This is how these problems start, everyone.
This is why I go always very late to bed, because I cannot sleep.
Tech watches something, and then before you know it, he's doing this kind of thing.
Yeah. And so basically, now we are on Earth. This is the North Pole. We are looking vertically on Earth. Yeah, Earth is rotating like this, and this is just 1 kilometer. We assume approximate as it is flat again. And here's our rotational speed, 360 degree in 24 hours. Okay, this is in order to calculate it. And this is our speed the bullet is flying. The bullet is flying with 2,000 kilometers per hour. I looked it up. It is between 2,500 or 3,500 kilometer per hour, but it becomes slower in reality due to air resistance. But we don't account for them. We assume it flies constantly now with 2,000 kilometers per hour in this direction.
Okay. So we're kind of making a little assumption there, because obviously we've taken away some wind.
Otherwise, it becomes air resistance is very complicated to calculate.
Yeah, we're at a level of complication that, like, some people probably
also
already.
Yeah, where flat earthers very often jump on it. Oh, you make assumption, you leave this out, you leave this out. In order to understand a problem, here you want to understand the Coriolis force. We don't want to understand aerodynamics. Yeah, so we break it down to the most essential points, basically. And if we want to have the other things, we can put them later on. Yeah.
It all works. It all works together, doesn't it? And that's one thing that people don't realize, is that you can have more than one force acting on an object at the same time.
Yeah, and in Germany, the weapons law are very strict, so I don't have the necessity to calculate also the air resistance inside, because I will never have the chance to use a sniper rifle. So okay,
don't think about what's going on in the world at the moment.
Rather not. And so if we calculate the Coriolis force, we had this formula in the beginning: 2,000 kilometers per hour down, rotational speed 360 degrees in 24 hours.
Yep.
We come to this minuscule value, 0.0808 meter per second, and Earth's gravity is 9.8, so much higher already. This is minuscule, and he's shooting only 1 kilometer. Doesn't make a difference. Here I had really a doubt, but okay, we continue.
So is that probably why sometimes you hear stories of snipers saying that they don't worry about Coriolis?
Exactly.
It's such a minuscule amount that it is.
You don't have to care about this.
You don't have to really. You'd be more worried and more concerned about wind, for example, if you're shooting over a kilometer, than you would about Coriolis. However, it is a part of reality, and that's why we're talking about it. And it is still valid, of course. And in manuals for snipe school, whatever you want to call it, that there will be details about Coriolis in there because of those reasons.
And if we basically, this is what I said. Now, this is Earth's gravitational acceleration, so it would be less than 1% of it. No, but if we do the math, if you calculate, we have SR is this length. No? So basically, 1,000 meter we want to shoot. No, we put in this should be VR by time in order to. This is basically the time velocity multiplied by time in order to get this one. And if we basically solve this equation for t, we get the time this bullet needs. And the time this bullet needs is 1.8 seconds. So 1 kilometer with 2,000 kilometers per hour in 1.8 seconds. And this is surprisingly long. This is 1.8 seconds.
You wouldn't know about it.
But is it enough for this little acceleration sidewards to have an impact? No? And we can calculate this. This is the acceleration sidewards, and it goes with this formula. I come later why this is the case. This is 1/2 the Coriolis force multiplied by time squared. And if you calculate this, you come to 13.9 centimeter. And if we have no wind, no other, no air resistance, you would miss by 13.9 centimeters. I don't know how big my head is, but you could definitely miss. So this is definitely a value you have to take in account already on 1 kilometer because of the Coriolis force, north to
Fantastic.
south. And
Well, we've been going nearly 2 hours now, Tech, and
really? Okay.
I'm sure
This is also
it's because there's so much to go through.
Yep.
Now,
Okay.
we
This
do
is
have a
basically
little
how
bit
it's
more to explain.
okay. I will make a slide of it later, not today, but in the next days, and post it under my account. No,
Hmm.
and here's basically all how this comes. It's calculated, and here's basically I post always with my calculation Excel table where all the formulas are also visible in written form mostly, and then also here so that you can basically type it in too, because unfortunately in X you can't attach an Excel file. Otherwise, I would do this. Yeah, and Coriolis force in action. This is basically the winds follow it too. Yeah, you have the winds going on the north to this side, and here to this side. And if you, this is satellite image of flat Earth. So basically a projection of Earth close to Mercator projection, and you see similar patterns like this. It's not 100% the same because of different heating of areas. Wind goes always from high pressure to low pressure, no? But it follows always these, here you see this one, these directions, not the Coriolis force directions. So we see it also here on the large scale and vice versa in the other direction. No?
Brilliant.
Oh, yeah. Okay, and this was basically the teaser for next time. Maybe we go. They say always gravity is fake. Yeah, gravity.
I said we were going to do it.
Yeah,
we're not frightened of gravity. We're gonna.
Yeah. So basically, and just a spoiler. Okay, today we looked only Newtonian physics. In Newtonian physics, for unknown reason, mass creates a force downwards, an acceleration downwards. And this force is mass multiplied by g. This is the acceleration of gravity. And this is Fg. And we feel an inertial force, when we sit, as if we feel the sit, the chair either below our butt. And so basically, this is the inertial force. And as long as you are not falling down with your chair, they are in an equilibrium or here on the ground. And this is basically gravity. Okay, gravity in Newtonian, for reasons unknown, gravity, mass attracts mass for unknown reasons. And in general relativity, for unknown reasons, mass curves space-time. But what does it mean? It means basically you are falling downwards. Instead of that the force is pulling you, the space with you is falling downwards and the ground is stopping you. So basically,
we'll get into that in a bit more detail next time, because it is quite technical and there's a lot to try and understand from it, isn't there?
Yeah, exactly. And so basically you are accelerated upwards. Here you are accelerated downwards, and here you are accelerated upwards. But the forces are in equilibrium. So basically you feel the same thing, but on the large scale, this is more precise than this. This is, and honestly, this is too complicated in detail also for me in engineering. So I'm electrical engineer. We learned only Newtonian. This is for Earth by far enough.
We'll give it a crack, won't we? We'll have a look at it. We'll give it a crack and see if we can work out which is which and how it affects
and why gravity is the most important thing. Is we show why gravity is not fake. Now this is, I think, for our next goal. And they say, what do they say? Gravity is because of buoyancy and density.
Buoyancy and density, which and then they stick in some electromagnetism for some reason.
And
there's lots of reasons why none of that works.
And next time we look basically into this one. So okay, this and in this one, so that was basically everything.
So
And
all of your stuff's available on your X site, isn't it?
yeah. So this
So
sorry.
you can
Sorry, this is
read
how do I close this? Yeah.
yeah,
Basically, yeah.
it's got an advert.
I will yeah, so basically this is my account. No, just type go to X, formerly known as Twitter. Elon Musk overtook it and called it X. And my name is TechTranslate, or my handle at TechTranslate_G. Then you find my account, and if you see this blue logo here, then you know it's me. And basically, if you go here to posts and to highlights, you find the most slides which I showed. No, and more will come. For example, why we see a lot of pictures of space, no stars, but sometimes, but on Earth we see it, and things like this, which are counterintuitive. Also here, I showed this one, also explaining the horizon. A lot of things which I showed, which are counterintuitive, and I think quite good explained. Sometimes go a bit deep in math, but yeah, this is basically. And we have this flat Earth Free Friday. So basically, what this
February.
means is
Yep.
we post about flat Earth. Most of us do it in this way. We post about flat Earth, but we don't interact with them. So basically, no replies to them, no engagement with the posts. I don't click on the posts anyway, because if you click on the posts, they get money from it, because most of their accounts are monetized. I'm not monetized. My account was by far too small, but we post something which triggers them to annoy them, but we absolutely ignore them this month, because it's also very nice, because you don't have to care about these stupid replies. Here, this guy, this is the greatest one. You know this one, no? This this is when I post why we can stars or not, I get this reply here: psychologically retarded. What is the altitude of sea level? What is the elevation of sea level? What is the depth of sea level? Okay, I don't read mentally. You are claim you are not mentally retarded. Hey, I never claimed that I'm not mentally retarded. Why? What? I never claimed
the depth of sea level. Okay, they understand that sea level is the top bit. Yeah.
He was following
okay.
me. Today I pushed him away from the list of my followers, because he is actively searching for me. He found me again and directly posting other my posts.
Hopefully, he'll watch this. He can come join us next time on the show.
Yeah, of course. I muted him now. I did not block him. I want that he sees my stuff, but normally if he replies, I see it in my timeline. Yeah. And he posts a lot of shit. I don't want to see this. And so I muted him. I'm not alerted it, but he can still view my posts. It's the first one I ever muted. So this is
that's good. But it's Flat Earth Free, or Flat Free February. So if you are, we recommend anyone joins in, don't give them the attention, basically, because a lot of them are just attention seeking, and like you say, they're trying to get clicks for monetization. And even if you reply to say you're dumb, that's actually giving them a reward. That's their monetized post. So just ignore them for February, and
basically on their post gives them money. Every click on their post gives them money. You're paid by engagement, and every click on it gives you money. And these accounts are very big. Here I have only 1,000 something followers. They have 20,000 or more. Yeah, and then you have enough engagement to get money from it. And the X algorithm prefers provocative nonsense. This is, since Elon Musk overtook it, the algorithm became worse, really. And nonsense get the most clicks. Yeah, and he says this is freedom of speech, but right now the algorithm prefers nonsense and provocative speech. And if you make something nice, the algorithm does not pick it up. And this is
hopefully people will pick this up and when they watch this at some point,
Yeah.
and they can see that you've done that. All of your details are obviously in the description anyway of this stream, so anyone can find that if they want to find
Exactly.
you, and therefore we can look at our next step, which is a big one. It's gravity. It's gonna be interesting. We may have to split it in two
Yeah.
parts. We've gone on 2 hours on an hour-long show, so maybe we should have split motion. But as you can tell, there's a lot to it, and it isn't always intuitive. Now, what I would say is, if you've got to this stage and you're still confused, either go back to the beginning, have another look at some of the earlier explanations. They may help bring it all in line with you to sort of understand some of the more complicated things behind it. We don't ever expect anyone to understand the full mathematics behind it. I don't. I'm first one to offer that I don't fully understand it all mathematically, but tech does, and that's the wonderful thing about reality, is there's people here who do understand it, and will be able to explain it to you. And these are our people that we should admire in a lot of ways. You know, that they've gone into a lot of education, they've understood the math, they've understand how everything works, and they can teach us to not be flat earthers.
Exactly.
So with that, I'm going to say thank you very much.
Yeah.
We look forward to next time. It's been absolutely wonderful having you here as always. I will give you a little gesture of goodbye and a take care, and we will see you next time. Remember to subscribe if you enjoy any of this. Obviously, hit the like if you're still around.
Yeah. And follow me.
And follow TechTranslate.
Yeah.
As always. Welcome to reality.
Yeah. Welcome. Thanks.
Welcome to reality.
Hello.